There we are.
Hello, everyone. Today we're reading BitNet Scaling One-Bit Transformers for Large Language Models. This is a paper that Microsoft brought out in October last year, and they have posted some updates. There have also been some other follow-up uh, research papers, but this week Microsoft have open sourced the code that implements this research paper. And so possibly on Thursday we might be going and doing a demo of that code. Um, yeah. So let's get into it. Wait, let me fill my glasses first. That would be a good idea. I don't think that worked. Yes. Okay. Abstract. The increasing size of large language models has posed challenges for deployment and raised concerns about environmental impact due to high energy consumption. In this work, we introduced BitNet and a scalable and stable one-bit transformer architecture designed for large language models. Specifically, we introduced BitLinear as a drop-in replacement for the NN.linear layer in order to train one bit weights from scratch. Experimental results on language modeling shows that BitNet achieves competitive performance while substantially reducing memory footprint and energy consumption compared to state-of-the-art 8-bit quantization methods in the FP16 transformer baselines. Furthermore, BitNet exhibits a scaling law akin to full precision transformers, suggesting its potential for effective scaling to even larger language models while maintaining efficiency and performance benefits. Um, for just for background, NN.linear is yeah, that's the layer that is in NN is a PyTorch package, and yeah, usually it's a 16-bit or 32-bit like data type depending on what hardware you're running on. Um, yes. And for Susila, we've only done this a couple of times with people on the call before. And so if you want to just like call out if you don't understand anything or ask questions, feel free to interrupt at any point. Um, yeah. So we will go to the other bit. I'm just looking at seeing what these are, but I
They're
think
basically like their marketing numbers, more or less.
yeah, that's a good
Of
point.
just like how much better the BitNet does versus the floating point 16.
BitNet has more loss, but it's higher. I don't know. It converges. Oh,
The
it seems
loss,
like
that's model side. Oh yeah, loss versus yeah.
yeah.
Interesting.
And what's this? Inference W bits. Training bits. Okay. Oh, right. It's just showing that it has one bit as opposed to quantization things. Uh, and then this one is it doesn't have a title. It has accuracy and weight bits. So I guess it's probably going to get to that at some point. An energy cost reduction ratio versus model size and bitnet. So the bigger the model gets, the higher the energy cost ratio reduction ratio, which is very interesting. So the bigger the model gets, the more efficiency gains you've got. Figure one, BitNet trains one bit transformers from scratch, obtaining competitive results in an energy efficient way. BitNet significantly outperforms state-of-the-art quantization methods. As the model scale size scales up, the cost savings become more significant, while achieving competitive performance with the models trained with FP16. I don't think there is anything unique about human intelligence. All the neurons in the brain that make up perceptions and emotions operate in a binary fashion. William Henry Gates III. Such a,
What a way to write his name, I would say.
and also what a way to start off a paper. Like,
Yeah,
okay, by that logic, absolutely everything operates in a binary fashion. So, okay.
wild.
Introduction. The rapid growth of large language models has led to significant improvements in various tasks. However, it is expensive to host large language models due to the high inference cost and energy consumption. As the size of these models grow, the memory bandwidth required for accessing and processing the model parameters becomes a major bottleneck, limiting the overall inference performance. Moreover, when deploying these models on distributed systems or multi-device platforms, the inter-device communication overhead can significantly impact the inference latency and energy consumption. That is a really good point. Model quantization has emerged as a promising solution as it can significantly reduce the memory footprint and computational cost of large scale models while maintaining competitive performance. Most existing quantization approaches for large language models are post-training. They are simple and easy to apply since it does not require any changes to the training pipeline or retraining the model. However, it will result in a more significant loss of accuracy, especially when the precision goes lower, because the model is not optimized for the quantized representation during training. Another strand of quantizing deep neural networks is quantizer-aware training. Compared to post-training, it typically results in better accuracy, as the model is trained to account for the reduced precision from the beginning. Moreover, it allows the model to continue training or do fine tuning, which is essential for large language models. The challenge of quantization aware training mainly lies in optimization, i.e., the model becomes more difficult to converge as the precision goes lower. Besides, it is unknown whether quantization aware training follows this scaling law of neural language models. In this work, we focus on binarization, i.e., one bit, which is the extreme case of quantization, applied to large language models. Previously, studies on binarized neural networks have mostly revolved around convolutional neural networks. Recently, there has been some research on binarized transformers. However, these studies have focused more on machine translation or BERT pre-training, which is quite different from large language models. For example, machine translation employs an encoder-decoder architecture. BERT pre-training utilizes a bidirectional encoder and large language models where I am
Lower.
getting mixed up.
For the second last line of that paragraph, furthermore, large language models.
Did I just have a stroke? Yeah, there we go. Um, Recently there has been a research on binarized transformers. However, um these studies have focused on machine translation or BERT pre-training, which is quite different from large language models. For example, translation employs an encoder-decoder architecture. BERT pre-training utilizes a bidirectional encoder, and large language models use a unidirectional decoder. Furthermore, large language models are typically scaled up to a much larger model size, while BERT and machine translation models do not undergo such extensive scaling. Um, I'm not actually so the encoder decoder architecture was the one that had that was introduced in Attention is All You Need.
No.
BERT, I'm not actually sure of the architecture of BERT. I,
Well, Bert's an embedding model, isn't it?
BERT is used architecture. It's an encoder only transformer architecture. Okay, that makes sense. Embedding encoder and task head, which is the same as a decode encoder. So it's an encoder, not a um for reference, um encoder only takes the original transformer was this one here, where the left side was an encoder and the right side was a decoder. GPT is a decoder only model and BERT is an encoder only model, which is confusing, but I think it just has to do with the type of like order that they put the multi-head attention in different ways that either makes it an encoder or a decoder model. Anyway,
Quick question. When they
yes.
say 1 bit, is that like one hot encoding or multi-hot encoding? Is that what they're doing basically?
That was no, it was saying the weights in the neural net are literally a 0 or a 1.
Yeah.
Okay.
With one hot encoding, you're spreading out data across across like the same number of bits, but you're doing it in such a way so that the pieces of data are equidistant or what's the other
Orthogonal.
orthogonal.
Yeah,
With this,
I think of one hot encoding like categories,
yes.
right? So if you have, for example, the you could, it's not the best example, but where I was going was the output token would be a one hot, at least what you're training for, where you get the input sequence and then the output label is a one hot of which token comes next. And then the model selects which token bit to match that. But this we're saying
Got it.
in this paper, the weights themselves that are learned are they do it in -1, 0, or 1. And I guess they call that 1.58 bits
Yeah.
with some entropy math because it really takes 2 bits to represent 1 or -1. But there's if you have 2 bits, that's 4 values, and they only have 3, so that's why they call it 1.58 bits.
Yeah, so
Gotcha.
usually you do it in powers of two. So there's two, two um 2 to the 1 or 2 to the 0, I guess. Uh does that make
It's because there's no -0. That's why they don't need all 4 bits.
Yeah, I will. Does would more explanation help, or do you think you understand it?
I think I got it.
Okay, cool.
Thanks.
Yeah. So, um, to the best of our knowledge, this work is the first to investigate quantization-aware training for 1-bit large language models. We propose BitNet, a 1-bit transformer architecture for large language models, which aims to scale efficiently in terms of both memory and computation. BitNet employs low-precision binary weights and quantized activations, while maintaining high precision for optimized states and gradients during training. Our approach is designed to be scalable and stable with the ability to handle large language models efficiently. The implementation of the BitNet architecture is quite simple, requiring only replacement of linear projections, NN linear and PyTorch in the transformer. Furthermore, it complements other acceleration methods for large language models, such as page detention, flash attention, and speculative decoding. We evaluate BitNet on a range of language modeling benchmarks, comparing with state-of-the-art quantization methods in FP16 transformers. Experimental results demonstrate that BitNet achieves competitive performance in terms of both perplexity and downstream task accuracy. More importantly, BitNet significantly reduces the memory footprint and energy consumption compared to the baselines. Furthermore, we show that BitNet follows a scaling law similar to that of full precision transformers, indicating that it can be effectively scaled to even larger models with potential benefits in terms of performance and efficiency. Bitlinear. Figure 2, a computation flow of bitlinear, the architecture of BitNet consisting of stacks of attention and FFNs, that's feed-forward networks, where matrix multiplication is implemented as bitlinear. So feed-forward network is just the part in the transformer that doesn't do the attention. So it's just like a standard neural network, essentially. Yeah. Um, so
Doesn't the attention have weights too?
yeah, attention does, but the way that I've had it described to me is that the attention block is sort of tending tokens to what other tokens to other tokens. So like if you say something like the blue duck, blue would tend to duck and duck would tend to blue. And like that they're like information transferring across different tokens. Whereas the feed forward network in would just be a standard neural network that then can sort of take that extracted information and then process it.
Right.
Yeah. So this and that, this and these are like exactly from it, like the original paper here. So if we go here, we've got this one that we've already seen, and these ones here are just like exactly the same.
Oh, wait,
So,
go back to that. So there's the linears. Go back.
yeah.
So it's just doing, oh, dot product. Okay, yeah. And it was saying, yeah, I don't want to jump ahead, but they were talking that when you're doing it in one bit, the multiplications become additions, which I thought was cool.
Yes. But oh well, it's not additions. It's bit. It's
No, so there's two matrix multiplications. So there is no weight in there. This is a good reminder.
well, it's.
Well,
I mean, it's not a weight more than it is. It's like a binary quantized weight or something. But then
yeah, I mean, even the
there's the
original
and.
version in the classic form, there's no weights in the attention head. It's all in the linears.
Um. Right.
Is it
So you're
better?
saying
Yeah,
that
it's
this.
right here. So so the key, it's query, key, and value are those
Yeah.
letters there. So the
Yeah.
query and the key get multiplied together. Scale, I guess, is just like a normalization type of thing. I don't remember what they do with the mask there, but it says it's optional, so we can ignore it. Softmax is a nonlinearity, and then you matrix multiply that result with value again. Cool. So there's no weights in the attention. That was my
Yes. Yeah. I will continue that. Two, BitNet. As shown in Figure 2, BitNet uses the same layout as transformers, stacking blocks of self-attention and feed-forward networks. Compared with vanilla transformer, BitNet uses bitlinear instead of conventional matrix multiplication, which employs binarized, i.e. 1-bit model weights. We leave the other components high precision, e.g. 8-bit in our experiments. We summarized the reasons as follows. First, the residual connections and layer normalization contribute negligible computational costs to large language models. Second, the computation cost of QKV transformation is much smaller than the parametric projection as the model grows larger. Third, we preserve the precision for the input-output embedding because the language models have to use high precision probabilities to perform sampling. So, in the grand scheme of things, they only did it to they binarized
the linears.
the linears. Yeah. So, uh, which is interesting, because there is another paper that actually went and then did they binarized everything. And then one of the things that they got out of that paper was that you can run it on a FPGA, a field programmable gate array, so that because everything is binary now instead of just the linears.
That sounds really cool to be able to, like, eventually I think we'll get to the point where you've trained a neural net and then you're writing it in, you compile it into Verilog and you send it off to a hardware manufacturer and they make you a chip that just takes in your tokens and outputs more
Mhm.
tokens.
I find this to be really interesting in like all things like, I don't know, networking or
It's a lot like the custom hardware in Bitcoin,
yeah, right.
where it started off with GPUs and then they got ASICs and then then they got FPGAs and then they got ASICs. Seems like it. This seems like an interesting path of
It's so
making it
cool.
hardware directly.
Bitly with the signum function following lop 22. Is this going to allow me to read it without clicking into it? No. We centralize the weights to be zero mean before binarization to increase the capacity within a limited numerical range. A scaling factor beta is used after binarization to reduce the L2 error between the real value and binarized weights. The binarization of a weight W element of the reals of dimension n by n can be formulated as W squiggly equals sine of W minus A tilde W tilde, not squiggly. Sine W sub ij is equal to +1 if W sub ij is greater than 0, or -1 if W of sub ij is less than or equal to 0. And alpha, sorry?
Didn't they have 1 + 1 0 and -1?
So yes, but this is just the sign.
Oh, yeah.
Yeah, so I guess this is yeah. If it's equal to 0, interestingly, they have a sign of negative, which I wonder if that's important. And alpha is equal to 1 on n times m multiplied by the sum of ij of w sub ij. We further quantize the activations to b bit precision. Following this, we use ABS max quantization, which scales activations into the range of negative Q sub B to Q sub B, with Q sub B equaling 2 to the B minus 1. By multiplying with Q sub B and then dividing the absolute maximum of the input matrix. X tilde is equal to the quant of X is equal to clip of X times QB divided by gamma, and negative QB plus epsilon and QB minus epsilon. And then clip XAB is equal to max of A and min of B of X, and gamma is equal to the absolute value of infinity.
I don't think that's what that is. I think it's the I'm trying the X is a vector, and so it has to do, isn't that the length of the vector?
Yes, that makes sense.
But I don't know what that subscript notation is. That seems. Where do they even use gamma? Oh, it's up there.
Yeah, so the quantization is we're taking our vector and we're multiplying it by this so we're quantizing it to our b bit precision, and so this is getting the ratio So we're scaling the matrix.
That's
Sorry, we're scaling the vector. Um,
So when they say activations, is that the input that multiplies to the weight, or is that the output after it's multiplied? I mean, I guess it doesn't even.
well, I guess that's after they I guess we'll I'm not completely sure, but like
Right,
with
we
this,
can keep
this
going
is
and
just
coming
a
back to
scaling factor
it.
on this is just a scaling factor on the uh on the
Right.
vector.
So
And
that's
then here we're taking the negative
B and X. Well, that X. Well, then I guess X isn't a vector then. Okay.
I'm just trying to so QB is the quantization that's the range. Okay, so that would be the lower one and that this would be the larger one. For where epsilon is a small floating point number that prevents overflow when performing the clipping. For the activations before the nonlinear functions, e.g. ReLU, we scale them up into the range 0 of Q sub B by subtracting the minimum of the inputs so that all values are non-negative.
I think I think what scroll back up to where it said some parts were the 1-bit and some parts were the 8-bit. I think that's what they're talking about here. Yeah, it's right there. So we leave other components high precision, example 8-bit in our script.
Right.
So this is the saying the stuff, the weights are just based off the sign, but the other pieces, we quantize the activations to B-bit or 8-bit precision. But it could just as easily be 16-bit, so that's why they leave it like that.
Right.
Which we use abs max quantization, which scales the activations to the range minus QB to plus QB, where Q is to the number of bits minus 1. So that's we scale activations to the range minus 257 to plus 257 if you have two or 157, 120 minus 127 and plus 127. That's the quantization for that. And then the clip just means that we scale, I guess, that gamma. I'm not sure what that gamma is on number 5. It's used in number 4 again. Sure.
Infinity norm or the maximum norm of X. In other words, Y is equal to the maximum absolute value in the tensor X.
Oh, I guess it's the max across all the elements or across all the training data.
This is used as a scaling factor in the quantization formula to help normalize the values before clipping them between negative QB plus epsilon. And the infinity norm is commonly used in quantization schemes because it helps preserve the relative scale of the values while mapping them into a bounded range suitable for quantization. So I guess across all x's,
Yeah.
it's saying get the largest. So across across all x's, get the largest value of that, and then squish that down to normalize that to 1. And then everything that's then below that would then be 0 or -1. Or B. It would be in the range B, so 8 bits or something.
Well, that's the max across all x's before the quantization because that's why we
Yeah.
Do that here. And then. So what does that look like? Is it transform? What do you think
Well,
the
so
shape of that curve looks
because
like?
the activations, if you don't quantize them, um, might because you're still using you like that depending on what
Yeah,
hardware everything
yeah.
can.
What I'm getting at is it does it create hard edges, like sharp edges, or is it smooth within the quantized range? I mean, I guess it's discrete anyways, but you know what I mean? So what would, if you put, say we're doing the 8-bit and you want to quantize like 200.
Well, it depends on the distribution of the rest of the numbers.
And your biggest X is 1,000.
Well, then I guess it would squish 1,000 to 200 to 8 bits 127,
Yeah.
and then it would squish
So you end up just multiplying your 200 over 127 divided by 1,000.
yeah 127 divided by um multiplied by 200.
Okay.
It'd be
So
25.
it does, yeah. Yeah. It's still linear.
Yeah.
That's yeah.
Um,
What a complex way to say it. So you linearly squish it.
this like as we said with the econ paper, to computer science people read something that has a slight bit of math in it. Um, so in the case of um the activations before the nonlinear functions, we scale them up into the range 0 QB by subtracting the minimum of the inputs so that the values are non-negative. X tilde is equal to quanta x clip of x minus, how do you n? What's this one again? Multiplied by QB on gamma, epsilon and QB minus epsilon, where the n is the minimum of x sub ij. Um,
The letter is eta.
et,
Et.
eta, gotcha. Um, so using, this is just going between, so we're subtracting that
It's
because
the same thing. So it's just so the it's
scaling the minimum of the inputs so
yeah,
that all values are non-negative.
yeah.
That makes sense. Because you're subtracting the minimum, it's going to then be positive. And so then it's going to be within the range that you want it to be in this one. In this work, we quantize the activation to 8-bit and leave lower precision in future work. Moreover, the quantization is performed per tensor during training, while per token during inference for both stability and efficiency. With the above quantization equations, the matrix multiplication can be written as y is equal to w tilde multiplied by x tilde. We assume that elements in w and x are mutually independent and share the same distribution, and w and x are independent of each other. Then the variance of the output y is estimated as var y is equal to n var of w small w tilde multiplied by x tilde, um, which is equal to n of the entropy. No, what's
It's expected value. If it's variance, it's
expected
expected
value
value.
of uh w tilde squared, expected value of x tilde squared, which is equal to n beta squared expected value of x tilde squared, which approximates the expected value of x tilde squared. Okay, that's variance. Why is the variance important? And for the full precision computation, the variance of the output var y is at the scale of 1 with the standard initialization method, e.g. Kaming initialization or Xavier initialization, which has the great benefit of to the training stability. To preserve the variance after quantization, we introduce a layer norm function before the activation quantization. In this way, the variance of the output y is then estimated as a var y approximates the expected value of the ln natural log? No, ln
I'm wondering something.
of x tilde squared being equal to 1, which has the same magnitude as the full precision
Linear norm, isn't it?
linear norm.
Layer
Yeah.
norm. That's what they're talking about here.
That
Yeah.
makes sense. Which has the same magnitude as the full precision counterpart var of y. In the context of transformers, it has to be the exact implementation as sublinear norm. With sublinear norm, the quantization methods above, we have bit linear, which is formulated as y is equal to w tilde x tilde, which is equal to w tilde quant of linear norm of x multiplied by beta gamma over q sub b, where linear norm of x is equal to x minus e of x divided by the square root of the variance of x plus epsilon, and beta is equal to 1 on n multiplied by m of the absolute value of w with the yeah with the other value being
Those
1.
double bars is not absolute value.
It is the
It was the
scaling factor
yeah.
in norm, in the 1 norm.
Yeah.
Figure 2 provides an illustration of computation of flow with bit linear. After the sublinear norm operation, the activations are quantized with the ABS max function. The matrix multiplication is performed between the 1-bit weights of the quantized activations. The output activations are rescaled with beta gamma to dequantize them to the original precision. This is just pointing back to this one here, right?
Oh, okay. I see. Hold on. Go back down.
Yeah.
So that's where the variance comes into it to calculate this.
Right.
The
Because you need to get the variance to calculate the
this seems like the kind of thing that's like 2 lines of code that would make it a lot easier to read than
yes.
the equations.
So we're taking the square root of the variance plus epsilon, and then and the x minus the x. I'm just gonna quickly chuck this into Claude. Claude's having trouble as well.
Did you do that or did it just not?
I refreshed.
You have to think on your own, whatever's, oh, never mind.
I can't think on my own. What are you talking about?
Okay.
Never. Lay normalization, the mean x, e of x from x. So you were subtracting the mean and then divided the square root of the variance plus a small epsilon. That makes sense. Which is interesting because I actually have written this code before.
Go back to Claude. Is that the mean across the just the vector or the batch or all the training data?
Layer in that particular matrix.
Oh yeah, I guess that makes sense because it's not connected to the training data immediately.
Yeah.
Yeah.
Um, Figure 2 provides an illustration of the computational flow of bit linear. After the sub LN operation, the activations are quantized with the ABS max function. The matrix multiplication is performed between the 1-bit weights and the quantized activations. The output activations are rescaled with beta gamma to dequantize them to the original precision.
I guess
Is that
that's the last part of equation 11.
that's the last pass to what?
Equation 11.
Ah, right. Because we're doing that. We're doing the opposite.
Yeah.
Model parallelism with group quantization and normalization. One essential technique to scale up large language models is model parallelism, which partitions the matrix multiplication on multiple devices. A prerequisite for existing model parallelism approach is that the tensors are independent along the partition dimension. However, all of the parameters alpha, beta, gamma, and eta are calculated from the whole tensors, breaking the independent requisite. One solution is to introduce one all reduced operation for each parameter. However, even though the communication for each parameter is small, the amount of synchronization is growing as the model becomes deeper, which significantly slows the forward pass. The problem also exists in sub LN, where the mean and the variance should be estimated across the partition dimension. To this end, we propose a simple approach that makes the model parameter parallelism more efficient. We divide the weights and the activations into groups and then independently estimate each group's parameters. This way, the parameters can be calculated locally dimensions, and each group has a size of n on g times m. We then estimate the parameters for each group independently. Alpha sub g is equal to g on n m multiplied by the sum ij of w sub ij to the g.
I think it's the group identifier.
Right. Beta sub g is equal to g on nm of the normalization
Oh,
of the one normalization of wg. So we're dividing it into g groups along the partition dimension, and then each group has the size of that, and then we estimate the parameters for each group independently.
yeah.
So
They're just defining an alpha for a group and a beta for a group.
yeah,
I don't think they've explained where they
you're
use.
not normalizing the entire thing. You're just doing it now, like within these little mini batches, basically.
Yeah.
Table Y, energy consumption of bitnet and transformer vary in different model size. Results are reported with a 512 with 512 as the input length, where W of G denotes the Gth group of the weight matrix. Similarly, for the activations, we can divide the input matrix X is a n times m vector into G groups and then calculate the parameters for each group. Gamma sub G is the infinity normalization of X of G, and eta of G sub G is min of Xij G. For layer normalization, we can apply the group normalization technique to compute the mean and variance for each group independently. Layer normalization Xg is equal to Xg minus the mean of Xg divided by the square root of the variance of Xg plus epsilon. In this way, we can efficiently implement model parallelism with group quantization and normalization, which requires no additional communication and can scale to large language models. Cool. So they just sidesteps the entire problem. Cool. Which is
By using the same equations.
Yep, but with a G in them. 2.2 model training. Straight-through estimator. To train our 1-bit model, we employ the straight-through estimator, STE, to approximate the gradient during backpropagation. This method bypasses the non-differentiable functions such as sine and clip functions. During the backwards pass, the STE allows gradients to flow through the network without being affected by these non-differentiable functions, making it possible to train our quantized model. Mixed precision training. While the weights and the activations are quantized to low precision, the gradients and optimizer states are stored in high precision to ensure training stability and accuracy. Following the previous work, we maintain a latent weight in a high precision format for the learnable parameters to accumulate the parameter updates. The latent weights are binarized during during the forward pass and never used for the inference process. I just realized my thing is not charging. There we go.
While the weights and the activations are quantized to low precision, the gradients and the optimizer states are stored in high precision to ensure training stability and accuracy. That makes sense. Following on the previous work, we maintain a latent weight in a high precision format for the learnable parameters to accumulate the parameter updates. Oh, okay. So they store, right. So while they're training, they're using full precision weights, but they're doing the binarization on the forward pass.
Gotcha.
That's how they train it. They're still training full precision matrices, but they're doing the binarization on the forward pass so that it learns to generate from the quantized weight.
And so this would mean that like the gradients are still in FP16 because trying to push a gradient through a 1-bit
Yeah. And they did mention that. So the gradients and optimizer states are stored in high precision to ensure the training stability and accuracy. But they also, when they say latent weights, those are the weights that they're learning. They just basically, when the training is finished, they get exported as the single bits. But over the course of the training, the weights themselves are in high precision and the gradients, optimizer states are in high precision. So everything's in high precision in the training. The difference is they're doing the binarization on the fly during the forward pass so that it trains proper forward. It trains to do it as binary weights, but there are no binary weights in the training process that are actually stored until it gets exported.
Yeah. Yeah. Yes, because then once you've trained everything, then you do some final export, and then you don't need to do the binarization every time because it's already part of the model. Large learning rate. One challenge for the optimization that it is that a small update on the latent weights often makes no difference in the 1-bit weights. This results in a biased gradient and update, which are estimated based on the 1-bit weights. This problem is even worse at the beginning of training, where the models are supposed to converge as fast as possible. To address this challenge, we explore various methods, concluding that increasing the learning rate is the simplest and best way to accelerate the optimization. Our experiments show that BitNet benefits from a large learning rate in terms of convergence, while the FP16 transformer diverges at the beginning of training with the same learning rate. More details can be found in section 3. Computational efficiency. We estimate the computational efficiency in BitNet in terms of both arithmetic operation, energy, and memory footprint. We mainly focus on the calculation for the matrix multiplication, since it contributes to the most to the cost of the large language models.
It contributes the most to the cost of the language.
Yeah. Arithmetic operation energy. According to the energy model in those, the energy consumption for different arithmetic operations can be estimated as follows. Bits add energy 45 nanometer, FP32 is 0.9, FP16 is 0.4, and int8 is 0.03. So we're using int8 in all
Oh,
of
these
that.
are, yeah, these are different types of CPUs.
Right.
So a chip made on a
So
45.
these are the
I
operations at the
yeah, I
top.
was wondering where nanometers came in, but cutting edge CPUs are made on a 7 nanometer process, and I guess the older ones are the 45 nanometer.
That makes sense. Um,
So my,
oh, gotcha. Um, that is interesting. Table 2, add and mole energy consumptions for different bit representations at 45 and 7 nanometer process nodes. In vanilla transformers for matrix multiplication with dimensions m times n and n times p, the energy consumption can be calculated as follows. E add is equal to m times n minus 1 times p times e hat add, and e mole is equal to m times n times p times e hat mole. For BitNet, the energy consumption of matrix multiplication is dominated by the addition operations, as the weights are 1 bit. The multiplication operations are only applied to scale the output with the scalars beta and gamma on Q sub B. So the energy consumption for multiplication can be counted as E mole is equal to M times P plus N times M times E hat mole, which is significantly smaller than in transformers. The energy savings of W1A8 bitnet compared to full precision 3232 and half precision 1616 transformers as shown in table 1. As can be seen, bitnet provides a significant energy savings, especially for the multiplication operations, which are the major component of the matrix multiplication energy consumption. So this is table 1. We've got bitnet being, yeah, really small.
I wonder if you'd be able to fine tune an existing model into being bit linear.
I think I think they have, if you go to the bitnet, they I'm not completely sure, but they have this one here, which is Llama 3 8B. Um I think this is a
Yeah.
1.8 bit version of it, which is pretty cool. Oh, and they've got a blog post too.
Let's go back to the paper and then come back to this.
Um where were we?
So we're talking about the energy efficiency based on.
Yes. Um
Interesting thing is, so how, I wonder how they actually do 1 bit calculations in practice, because you can't access 1 bit of memory at a time. You have to load all 8. I mean, I guess you just load up
But
8.
this is, I think this is why in this one here, we're using int8 to represent it.
Yeah,
So I think it might be the case that even though it is
but how,
even I'm suspecting that even though they call it bit 1.58 bitnet 1.58, they're actually just using 8 bits. But because
not necessarily to store it on disk, so there's that. Like but this doesn't. Oh, no, the difference is you're doing integers versus floating points.
yes.
That makes a huge difference. I bet if you could just do integer versus integer, that like an int32 would be way more efficient than a floating point 32.
Yes. Yeah, because with floating point addition, you need to normalize the mantissa and then be able to actually add all
Yeah,
of the um
but why is floating point 32 so much harder than a floating point 16?
um because the range in like the IEEE 754 standard ends up you need to do fun fact, this was actually my first project as a software engineer. I was implementing the decimal standard for this.
Yeah, your first project was at the IEEE.
No. I was implementing a
Yeah.
standard this Ingo. It wasn't for IEEE. Man, that would have been awful. Um so binary 16, half precision. Um you've got 11 significant digits. And binary 32, you've got 24. Um maybe it has to do with the like the number of clock cycles or something that it takes.
That could, yeah, all right. It just, one thing that caught me by surprise until I was looking at it for a little bit is its floating point integer.
Yeah.
So if you can just do things as integers, that'll be more efficient than floating points.
Yes. Yes.
All right, that's that.
I am actually curious because the what I said about like how many clock cycles, I think they're actually the same. But
Yeah.
I think when we're talking about energy, then
That's the weird thing is like, isn't it just built into a CPU to be able to multiply floating points together?
yes, but I think because we're talking about energy here, like it's the same clock cycle, but you're still passing in twice the amount of data in a floating point 32 compared to a floating point 16. And
But
that's
is it all
representing
just 16-bit registers?
uh
I guess
yeah,
you're
but
doing, I guess you're doing 2 at a time or 4 at a time.
yes. Which is why, but like currently we're just talking about energy and nothing else. And so if you double the amount of bits, or double the amount of registers, you're going to be approximately doubling the amount of energy.
But that's what I'm saying is I think the way they probably got this is there's one CPU instruction that'll multiply two 32 bits. And there's a second CPU instruction that'll multiply four 16 bits. And then divided that by 2 or by 4. Because I don't think a modern CPU.
Modern CPUs wouldn't have FP16 floating point
That's what I
arithmetic,
mean.
but like they would be probably
That being said, actually, we're talking about CPUs, but I think GPUs do have adjustable precision. Because they do everything on like 512-bit buses now. That if you divide into 32 bits or 16 bits or whatever.
the other thing about this as well though is a lot of the times I think with when you're moving from CPUs to GPUs with floating point arithmetic, a lot of the times they actually end up not needing to do a lot of the rounding.
Do those, do those
module.
papers have links?
Yes. There's this one and this one. It looks
That's cool. It's gonna be a bit of a rabbit hole to go on. So that's
yeah, that definitely is. I do like going. I would like to go down that rabbit hole though. Maybe we should just do like a hardware or actually to be fair, that's just the paper on on what was it? The other transformer one. What's the what it's I'm blanking. The state space models. Mamba 2. Really good one. And that goes into like the hardware optimizations and the way that they do certain mathematical tricks so that they don't need to expand a sequence because that would be happening at a slower level of memory than if they like do this cool trick or something, which then speeds up by a whole bunch of time.
we have a section in the forum now for papers.
That's cool.
So as we get all these links, we just make a new post for them and we'll collect
That's
them.
cool. I do like that. Okay. Comparison with FP16 transformers. Setup. We train a series of autoregressive language models with BitNet on various scales ranging from 125 million to 30 billion. The models are trained on an English language corpus, which consists of the PILE dataset, Common Crawl Snapshots, Real News, and CC Stories dataset. We use the sentence piece tokenizer to pre-process the data, and the vocabulary size is 16K. Besides BitNet, we also train the transformer baselines with the same dataset and settings for a fair comparison. More details can be found in the appendix. Inference optimal scaling law. Neural language models have proven to scale predictably with vanilla transformer architecture. The loss scales as the power law with the amount of computation used for training. This allows us to determine the optimal allocation of a compute budget as well as predict the performance of a large language models for smaller models. To study the scaling law of binarized transformers, we start by plotting the scaling curve for both BitNet and FP16 transformer baseline against the parameter count. We fix the number of training tokens and vary the model sizes. Figure 3 shows that the loss of the BitNet is similar to the FP16 transformer, which follows a power law. We then fit the scaling law with an irreducible loss term. L of n is equal to a times n to the b plus c. Figure 3 scaling curves of BitNet and FP16 transformers. They go down. And the loss of BitNet is the loss of BitNet for the same
That one's energy consumption.
energy consumption is less. So
What if
it's
why are
more
they
efficient.
10 to the 10 picojoules? Give that to Claude. What's 10 to the 10 or 10 to the 12 picojoules in kilowatt hours?
10 to the 10 picojoules
I assume those are picojoules,
in
kilowatt hours
wouldn't it just be kilowatt hours?
or kWh. Yeah, that's fine. That's not right. I think it needs to be, go back to the paper. That also doesn't seem right. Go back to the paper for a sec.
Oh, that's peta, not pico.
Yeah. But I don't think it's petajoules. I think it's, but picojoules doesn't seem right either because a joule is really small.
That is true. Mm, yeah,
Alright,
I'm not sure.
let's keep going. So,
To evaluate whether the scaling law can accurately predict the loss, we choose the models from 125 million to 6.7 billion to fit the parameters in the power law and use the law to predict the loss of 13B and 30 billion. It shows that the fitted scaling law predicts the bitnet's loss with high accuracy. Besides, the gap between bitnet and FP16 transformer becomes smaller as the model size grows. While the power law above measures the trend of the scaling of bitnet, it does not properly model the relationship between the loss and the actual compute. Previous work estimates the compute by calculating the flops. However, it does not apply the 1-bit models where cost is dominated by integer computation. Moreover, it mainly measures the training computation rather than the inference. To have a better understanding of the scaling efficiency of neural language models, we introduce inference optimal scaling law. It predicts the loss against the energy consumption. We focus on the inference energy cost as it scales with the usage of the model, while the training cost is only once. We estimate the energy consumption as in section 2.3. Figure 3 shows the scaling curve against the inference energy cost at 7 nanometer process nodes. It provides that BitNet has a much higher scaling efficiency. Given a fixed computation budget, BitNet achieves a significantly better loss. Meanwhile, the inference cost is much smaller to get the same performance as the FP16 models. Results on downstream tasks. In addition to the loss, we are also concerned with the capabilities with the scaling of BitNet. Compared to the loss, the capability is more difficult to predict due to the emergent nature of neural language models. To evaluate the capabilities with the interpretable metrics, we test both the 0-shot and 4-shot results on 4 downstream tasks, including Hellaswag, Winograd, Winograd, and Story Close. Figure 4 reports the average result in BitNet and FP16 transformer with various scales. Similar to the loss scaling curve, the performance on the downstream task can scale as the computation budget grows. Besides, the scaling efficiency of capabilities is much higher than FP16 transformer baseline in terms of both 0-shot and few-shot performance. Stability test. The major challenge for training low bit transformers is the stability and optimization. Therefore, we perform stability tests for both BitNet and FP16 baseline by training a series of models with varying peak learning rates. Figure 5a illustrates the results of the stability test. It shows that BitNet can converge with a large learning rate while FP16 transformers cannot, demonstrating better training stability of BitNet. This advantage in optimization enables the training with larger learning rates. Figure 5b shows that BitNet can benefit from the increase in learning rate, achieving better convergence in terms of PLL.
what's PLL?
PLL is peak performance loss. Peak.
Definitely not private pilots, I see.
Perplexity.
Oh, okay.
I don't know why they couldn't just say perplexity, but okay. Also, why is it capitalized?
Yeah.
Inference energy consumption. So BitNet is more efficient for any given energy consumption, which is cool. That's really cool. zero shot left and few shot right performance in bitnet and FP16 transformer against the inference cost. So this is right. So this is the perplexity, and then it starts going down, and then it starts going up because it's not doesn't have training stability. This seems cherry picked to the point where they already mentioned the fact that they needed to do stuff with the learning rate to make bitnet converge, and now they're saying that when you use the same learning rate, it then FP16 transformers don't converge.
I guess, but it's also, it seems like this to me almost seems like an optimal form of a neural net, even just in general. It's like the extra bits get in the way versus the structure of having the weights that represent hidden variables. So in its simplest form, you have lots of variables that are binary.
Yes.
The thing that I
Yeah.
didn't get is are they actually using 0, or is it just 1 or -1?
No, well, zeros. I think zero is important. I think they are. I think they are using zero.
Because the weights, we can come, yeah, go back up, because the weights were just meant to be the
Oh,
W bar. That was just set W tilde. That's just the sign.
yes. But so they're only no. No. It's not just the sign, but the weight the way that they the way that they um the way that it is binarized so is by looking at the sign of the FP16. So if the FP16 is positive, if
Yeah.
the sign of the FP16 is positive, then it'll have a +1. If it is negative, it will be 1. And if it's 0, then it will also have a sign of +1. So I missed that before and got that incorrect, but yeah.
Yeah. So the weights are 1 bit. First, we binarize the weights to either +1 or -1. So
Yeah.
during training, there's the latent W that's full precision, but the forward pass does the bit linear. But then as it's doing the backward pass, it's doing back propagation on the full
Yeah.
precision weights.
Yeah.
But the forward pass is only on W, which is just the sign. And then the alpha there, that's just for normalization, right?
Yes.
So, okay, we were page what, 8? Forgot what that came up from.
Um,
So we're
I think we had
because we passed on this, we were talking about stability. Yeah, keep going. We were here.
yeah. A comparison with post-training quantization. 4.1 setup. We train BitNet with the same setup as described in section 3.1. We compare BitNet with state-of-the-art quantization methods, including ABS Max, Smooth Quant, GPTQ, and QUIP. These methods are post-training quantization over an FP16 transformer model, which follows the same training setting and data as BitNet. Among them, ABS Max and Smooth Quant quantize both the weights and activations, while GPTQ and QUIP only reduce the precision of the weights. We apply the methods to various quantization levels. For the weight-only quantization, i.e. GPTQ and QUIP, we experiment with
Weights for activation 16.
W4 activation 16.
Yeah, so the weights are 4-bit, activations are 16-bit.
Right.
I don't know why they write it like that, but
To A16 for weight and activation quantization and ABS max and smooth quant, we use them to quantize the FP16 transformers to WA8 for W4A4 and W1A8. Our implementation of BitNet is binary weight 8-bit activation, which has lower or equal bits than the baselines. Results. Table 3 presents detailed comparative analysis of zero-shot performance of our proposed method, BitNet, against various baseline approaches on 4 benchmark datasets, namely Winograd, Story Clues, and Hellswag. All models have model sizes of 6.7B for a fair comparison.
I don't want to be that guy, but they said they had less bits, but they're using 8-bit activations and Smooth Quant only has 4-bit activations.
That is true. That is true. So, but like if you there's still all in all, yeah, they're using less.
But I mean, the weights are much bigger than the activations. So the 4-bit weights will still use a lot more data than
Mm-hmm.
weights, even if the activations are quantities.
Figure
The
6.
activations only live in memory, but the weights have to be like loaded in and out of the GPUs.
Yeah.
They represent based on that's the
And the activations scale with the context size and the weights scale with the size of the
number of parameters.
number of parameters, but if you want to be like smart about it, you can also do the number of layers because Llama CPP has a way of like M mapping the particular layer that you've got so that it doesn't load all of the weights into memory at the same time, which is pretty neat. And actually that's why one of the GGUF library was written because it's got a different tensor format to TensorFlow. Oh no, to PyTorch and TensorFlow so that it can do that more efficiently, I think.
I wonder if you could do that with the 1-bit weights.
Yeah. Yeah, that's true.
Oh, scroll down. Let's look at the results.
Yes. Um, well, what is yeah. Figure 6, zero shot and few shot results for bitnet and post-training quantization baselines on downstream tasks. So transformer is best overall, but bitnet is not far off, and quantization is a lot worse. Zero shot left, a few shot, yes.
Random in there.
Random quantization.
Just random quantization.
Or they just had random, I think maybe random weights.
Oh, wait, what?
So they were just showing that if you had a, does that make sense? I'm not sure.
But this is the accuracy of
On
picking.
downstream tasks, so random should definitely not be at 45% or something.
And it's picking 1 in 16K tokens. That's what they're measuring, right?
What do you mean?
Well, they had a vocab size of 16K. They mentioned that at the beginning.
Yes.
No, okay, I don't know.
I'm not that maybe that's random weights, maybe that's random tokens or something. I'm not sure. Which is interesting that there's quantization that gets worse than random. A lot of it actually. Um
Yeah.
Table 3, zero shot results of bitnet and the baselines PTQ post-training quantization, WGE Winogrand, WG Winograd, SC story clues, and HS Hellaswag dataset. So we've got WBits bitnet has complexity of 17.07 and lower is better. And we'll, I guess,
Lower is better, and the guys beside them are 3.5 times 10 to the 23.
yeah,
All right, doing all right.
yeah, it's not very good. Random, they didn't even put the oh, so maybe that's random token. So they're showing that that's interesting.
Let's walk through, like, go back to the Claude explanation of perplexity for a second. Interesting. The model is as confused as if it had to guess from 10 equally likely options. Okay.
I did not know that that was the interpretation. I knew that this part was the thing, but I didn't know that this was the interpretation of it. That's cool. So the complexity of bitnet is 17, whilst the standard transformer is 15, and that's the average across all of the choices, which is cool.
And that's for a given number of parameters, not for a given like file size on disk of the model, which is kind of interesting.
Well, I mean, complexity tends to get smaller as. Wait, sorry.
Yeah, as you have a higher capacity model, you'll have better complexity. That makes sense. But I'm just saying they're isolating it for the number of parameters, but you could also isolate it for the number of weights of bits.
Right. Gotcha.
The number of
Yes,
bits of
right.
weight.
And so instead of this being parameters, you would have.
Yeah, like there's a case to be made that you can compare the 6.7B bitnet to the 1.3B transformer because they represent the same amount of model size. But
Yes, even though there are more parameters in.
yeah, like
Yeah.
if you can fit more parameters in the same amount of data.
It's but like I find it interesting because it's like doing bitnet is similar to almost just scaling up the number of like connections that you've got.
Well, that's the whole thing. If you've got enough compute for n parameters, then you might as well just multiply it by 8 and use 1 bit instead of having 8-bit parameters or 16-bit parameters.
Yeah.
Like you're much better off having 16 1-bit parameters than having one 16-bit parameter.
Yeah. Yeah. Which is pretty cool.
Yeah.
The methods are evaluated across several bit levels spanning from 16 down to 1. Besides the zero-shot accuracy on the downstream task, the evaluation metrics include language model complexity on the validation set, which provides a comprehensive understanding of each method's performance. The results demonstrate the effectiveness of BitNet in achieving competitive performance levels compared to other baseline approaches, particularly for lower level bits. The zero-shot scores of BitNet are comparable with the 8-bit models, while the inference cost is much lower. For the 4-bit model, the weight-only quantization methods outperform the weight and activation quantizers, mainly because the activation is more difficult to quantify. BitNet as a 1-bit model significantly achieves better results than both the weight and activation quantization methods and the weight-only methods. As for the lower bit models, BitNet has consistently superior scores over all baselines. This proves the advantage of the quantization-aware training approaches over the post-training quantization methods. Figure 6 summarizes both the zero-shot accuracy and the few-shot accuracy for our method and baselines while scaling up the model size from 1.3B to 6.7B. It proves the advantage is consistent across all different scales. Table 4, aberration in BitNet, WGE Winograd SC story close, an HS HelloSwag dataset. Elastic is an activation quantization from bit robustly binarized multi-distilled transformer, while BMT is the architecture from binarized neural machine translation to stabilize the training of low bit models. So it's good, is what it's saying. It's got the best in all of, not this one, but that seems to be pretty close anyway. Almost got the most in that. I don't know the difference in these models, honestly.
They're all okay. Explain the ablation.
I guess we're gonna go on to that. I don't know why they had it here though.
I've
So
noticed they have tables in weird places in this PDF, but that's fine.
also, I guess they've also got indented. So I guess this is BitNet. This is BitNet overall.
Yeah.
This is
Okay.
with different sections. So in table 4, we present an ablation study from of our compared with several alternative approaches. We ablate the effect of our choices in activation quantization approaches as well as the techniques to stabilize the model training. BitNet implemented ABS Max to quantify their activation and use sub and LN for training stability. One quantization alternative is the elastic function, which dynamically adjusts the scale with learnable parameters. In our experiments, we find that ABS Max has better performance than the elastic function. Besides, the ABS Max function leads to more stable training, which enables a larger learning rate for BitNet. We further compare sub-LN with the pre-LN and the BMT architecture. Pre-LN is the default architecture for GPT training, while BMT is proven to improve the stability of binarized models. Our experiment showed that sub-LN outperforms both pre-LN and BMT. Therefore, we choose ABS Max and sub-LN as the implementation in BitNet. Conclusion, future work. We present BitNet a novel 1-bit transformer architecture for large language models. Our approach is designed to be scalable and stable with the ability to handle large language models efficiently. The experimental results demonstrate that BitNet achieves competitive performance in terms of both perplexity and downstream task performance, while significantly reducing memory footprint and energy consumption compared to other baselines. Moreover, BitNet follows a scaling law similar to that of full precision transformers, indicating that it can be effectively scaled to even larger language models with potential benefits in terms of performance and efficiency. The future, we would like to scale up BitNet in terms of model size and training steps. We are also interested in applying BitNet in other architectures for training large language models. Yeah. So
Go down to the appendix. Hyperparameters. Okay. Wait, hold on. Go back up. So training updates. Okay. Okay. For them? Yeah, okay.
That's all.
So I'm curious. Scroll back up again. Do they have, so training updates and tokens per sample? You think that if you multiply those two, that would be the number of tokens they trained on?
No,
No.
because
I'm trying to get a sense of how much energy and time they spent training these models.
well, they don't you don't do weight updates on every token.
No.
So the training updates, I don't know what if that would be like the training updates.
So wouldn't that be,
Maybe
guess-
training updates is the amount of total weight updates.
yeah, that's what I'm getting at. And then the tokens per sample. That's how many tokens they look at before dating the weights.
Oh, right. Um, but so
So what is,
we still need to know how many well, then it would be 256. No, actually, I'm not sure. Maybe. Um,
scroll up again? Okay. Like, I wonder what it would take to train a 125M model.
is this in like
With the 1 bit, the way they have it here, like how much?
doing some quick like back with the napkin math? The 125M model is one that Karpathy ended up posting in one of his State of the Union addresses on his LLM.c repo. It was, I'm not sure like the level of I'm not sure about the level of I don't know, joules or anything, but there was this one.
Okay.
LM.C 124 million, 90 minutes for $20. Yeah.
Ah, okay, so it's an 8x 100 A100 80 gig.
Yeah,
That's fair.
which is pretty cool.
Yeah. So I could do it with the 4090 and it would take a day.
Yeah. And
would
so if you then take
So let's get, is that linear?
sorry, this here.
So go back to that page you had. So 124M
Yeah. I'm
is
not so you're saying like if you have a twice
it,
the amount of model size, does the computation increase by 2?
yeah.
Don't I wouldn't expect it to, because as you double the parameter sizes, I think
I
the
mean, you also shrink the batch size, so you go through the data slower. You have more to learn and you go through the data slower.
Yeah, and then the convergence is slower as well because
Yeah.
you've got twice the amount of parameters to do, which means you've got twice the amount of weight updates, and so then um at the end of each weight like batch, you're going to be converging less than half as an intuition, not a like rule from what I can.
What does Cloud have to say? An interesting question.
Okay, so
So
it's
how,
wishy-washy.
yeah, so maybe just in general. So how does the train time, what or in general, how does the train time scale with the number of parameters?
Yeah. Chinchilla scaling law paper would actually be a really interesting one to eventually go through.
Yeah, put it in the form.
Yes. Yes, yes, yes. Does that form have an API?
It does. You can set up API keys.
That's cool. It would be cool to like hug, I set that up to either
Oh,
Twitter
I see what you mean.
or Face
Yeah.
Daily Papers or something.
So go back to Claude. So if you say if 125 M parameters takes a day, you're not typing. How long would it take for 1B or 10B?
Nice.
Yeah.
Um, a lot for that.
Yeah. I mean, 2 months is conceivable, but not 6 years.
At that point, I think we upgrade.
Yeah.
Yeah.
Yeah, I guess the question is if the training time will take longer than the useful life of the hardware. That's kind of cool. I don't know. Let's be clear with it.
One of the things that I always find though with doing experiments and everything with this is like the feedback loop of machine learning and everything is just ridiculously large.
Yeah.
Whereas like in software engineering, you write a unit test and it fails in 0.1 second. And so then you can just iterate on it really quickly. But no one's
Oh, I see what you mean. Yeah. But it's interesting that you say that it's a long feedback loop, which it is in terms of training stuff, when the field is still going ridiculously fast.
yeah, but this I guess this is like imagine if the developer tools around model development were the same and the practices were the same that we have in software engineering.
It is software engineering. It just has a long training cycle.
Yeah, I know, but like no one's uh I feel like there's a lot of solutions there so that you can do like hyperparameter sweeps and everything, and it just approximates what it would be so that it cuts down on the search space of possible areas that you actually want to investigate by estimating relationships in like the hyperparameters and the training time that humans would have a really difficult time actually estimating.
Yeah, I mean, if we have AI to do it, then it'll be
Yes. Yes.
Well, that was cool. That was
Um, and so like I don't want to read through a full other paper, but there were two other papers that were published that
the other thing. Do you want to pull up the link of the code the infants
oh
for
this one, yeah.
take a look at that. More
So
detail.
there's a energy cost is down 55% on the 700M model, and the 70B model it's down 70%. And
Oh my
what
god.
is the reduction in inference speed is up from 434 to 593, so 1.37.
Oh, okay, yeah, but they're kind of
They haven't mentioned
the small ones. The small ones are generating garbage faster than you can read it, but the bigger ones are still very fast.
yes.
I love
They're
how
not
they have
they didn't
human reading
mention the
speed.
loss though. There's nothing that they're not mentioning the loss between them,
No,
which seems a little sus.
but this is kind of wild that it's generating 52. Like the 7B is generating 52 tokens per second on a CPU. Just go down to the Intel. The 7 is still 18 seconds on. This seems like something that should be on a log scale. Um, but hey,
Yeah, this is pretty cool. Oh wow. That's sick. So they ended up posting update paper. Um,
this is the one I just read, right?
no. So this is the one that we just read went through like the background, like the introduced the concept of bitnet. This one here is uh r- recent research such as bitnet is paving the way for a new era of one bit large language model. In this work, we introduced one bit LLM variant named bitnet B 1.58, in which every single parameter or weight of the LLM is ternary. It matches the full
Oh,
precision
okay.
transformer LLM with the same model size and training tokens in terms of both perplexity and task performance, while being significantly more cost effective in terms of latency, memory throughput, and energy consumption. Um, More profoundly, the 1.58-bit LLM defines a new scaling law and recipe for training new generations of LLMs that are both high performance and cost effective. Furthermore, it enables a new computation paradigm, and opens doors for designing specific hardware optimized for one-bit LLMs. This one doesn't actually go through a whole bunch of background in
I see. Okay,
how,
yeah,
which
this
is
was the
why I
paper.
chose to read the other one. But yeah.
This was the paper I had sent you, and then we read a different one.
Yes,
That
that's
makes
exactly what happened.
that's what.
But
Okay,
this one doesn't actually make a whole bunch of sense unless you've gone through the first one to start with.
that's totally fair. No, I think that was the right call.
Yeah.
Uh,
Because people often show the diagrams of this, and it doesn't really the implication of this doesn't really make sense. Um, and then on top of that, there's another one called Matmol Free, um, which is someone else that then took this and then did a whole bunch of other stuff in turning it into um I can't remember exactly what was the difference between this, but it did it. I can't remember what was different between this and the Matmol free one. I think they might even go through it. Bitnet. Yeah. BitNet retains the self-attention mechanism, which relies on expensive MMM. Dynamically computated matrices Q and key are multiplied into the form of the attention map. Since both Q and K matrices are dynamically computed from pre-activation values, achieving optimal hardware efficiency on GPUs requires custom optimizations, such as specialized kernels and advanced memory access patterns. Despite these efforts, such matmul operations remain resource-intensive on GPUs as they involve extensive data movement and synchronization, which can significantly hinder computation throughput and efficiency. In our experiments, ternary quantization of the attention matrices in BitNet cause a significant drop in performance and failure to reach model convergence. This raises the question, is it possible to completely eliminate matmul from LLMs? So it seems like this is only going on the original matmul, but not the... Oh, no, it is also referencing that. So this is saying that the BitNet 1.58 still uses matrix multiplication, but not in but in like only some of the aspects. I guess that is what it's
I
trying
mean,
to
yeah, this is kind of interesting because for a single bit, a addition is an or, and a multiplication is an and. The only time it doesn't work is when you need to carry multiplication. Or I guess carry in addition to.
I guess you just round. Well, yeah.
But for that's the whole thing, is that for a single bit. I mean, I guess that's still a matmul though.
Yes. Um, this is also an interesting paper to go through, and I think we should probably do that at some point. Do
It'll
you
be
have,
interesting. I wonder if they tried doing +1 and 0 instead of +1 -1 in the
I
first.
think maybe I think like at that point, one of the problems might be that like a parameter can only then go negative, go positive or zero.
Mm.
And then there's no way of encapsulating a negative correlation between two like parameters. So if there's
I
like
wonder if you could use exclusive or though.
that is true. But I guess can't you just simulate every single logic gate with an exclusive or at that point?
Well, that's the whole thing, is that because that gets really cheap to do in hardware
Yes.
if you're just building exclusive ors.
Yeah. Um, what do you think about
What is a BF16?
binary float 16? It's different to a FP16 because that is the IEEE standard, and I think BF16 is BF16 is one that they use in um like GPUs or TPUs.
Okay.
Lower precision, high, yeah, FP16. Yeah.
I guess that makes sense if you don't need to go to, 10 to the 38 in the model weight, because then it just explodes anyways.
Yeah, and I guess like the extra exponent bits in the BF16 encapsulate that you want the same number of precision across more like exponents, as opposed to having less precision or like larger range. No, sorry, as opposed to having smaller range, but then higher precision. Because like when you have a higher precision and a smaller range, if you then have numbers that fall outside that, there's some clipping that gets done on the like upper and lower bounds that happen, as opposed to if you lower precision from everything whatsoever, you can then have more average precision across all of your numbers, which seem to be more important when you have a large set of numbers that are all within the same like category. Whereas the IEEE standard was specifically designed to be like the most generalist approach to
Yeah, well, that makes sense.
numbers.
That makes sense. What is the
Yeah.
B?
Sorry.
What is the B?
I think it's brain floating point.
Brain.
Yeah, these guys.
Cool. Wouldn't have guessed that.
Yes. So
All right.
that's that.
Yeah, we're about up on 2 hours.
Yes, there are many a more paper to read.
Yeah,
Maybe we'll do that. Maybe we'll not do that.
we'll get there.
Yes, but on Thursday it would be cool to go through that the Microsoft repo.
Sure. Yeah.
Cool. Good sesh. I guess that's that. And we'll catch you later.
Bye.